case is if the A is less than or equal to 1, and then the recursive case is the else, because it can continue, it calls it upon itself.
Perfect. Okay, so definition of the base case. It's the part of the recursive function that causes the recursion to stop. When this occurs, no more recursive calls. This is akin to the terminating condition in a loop. Okay, without the base case, you get infinite recursion, which is a thing. Okay, most compilers have a built-in limit. It'll shut off after like 255 consecutive recursive calls without anything happening. And it'll give you a warning like, you probably did something wrong here. Okay? The other part is the recursive case. This is the part that actually has the recursive call in it. Okay? There will always be both. There will always be a base case and there will always be a recursive case. Now, what you might find is the base case is the absence of a recursive case. So if we had a condition that said if something, then make a recursive call, and that's it, the base case is simply when the recursive case doesn't occur. Okay, so it's whatever condition it is, the opposite of that. Okay, so sometimes the base case is there, it's just invisible, if that makes sense. Okay. What were the two examples we used to demonstrate recursion last class? Who remembers one of them? Something about employees. Okay, true.
We did something last class?
Fixing the hole in the wall.
And then fixing the hole in the wall. Okay, so what we talked about was with the employees, we have the CEO at the top, and he wants a report printed. And so what he does, instead of printing the report himself, he calls the regional manager, says, hey, can you print me a report? Okay. Regional manager says, I don't want to print the report. I'm going to call the district manager. District manager picks up the phone, hey, can you print me a report? Meanwhile, the CEO is just waiting. He's just hanging out in his office. Regional manager's hanging out in his office. District manager calls the office manager calls the intern finally prints the report. All the while, everyone else that has made the call, they're just waiting. Okay? Intern prints the report. Now, when the intern gets the report, who does he take it to? Does he take it to the CEO? No, he doesn't take it all the way back to the first call. He takes it to the office manager, because the office manager is the guy that called it. Okay, so when we return from recursive calls, we always go back to the place that we were called. Not the original place, but to the exact place that we were called. Okay? Yes, sir?
Well, one thing I was wondering, it seemed like most of the recursive methods were stacks. That last question on homework, would that not be considered a stack since you don't want to do anything else after it ends?
In terms of a stack, all recursive calls are stacks. Okay? But in terms of what happens afterwards, it can be different things. Okay? Yeah, but whenever a method or function is called, it gets placed on the call stack. And the method that's on the top is the one that's always currently executed. Okay? Same situation with fixing the hole in the wall. Okay, we kept trying to do stuff. Each time we tried to fix the next thing, our tool broke, and we had a chain of things that we had to fix. And we couldn't start working on anything until we finally got one thing fixed. And then we could go back and fix the next thing and fix the next thing. So what I want you guys to remember from last class is that when we have recursive calls, we get this unfolding occurring. That unfolding continues until the base case is reached. And then we fold back up until we get to the original. Okay? Any questions on that? All right, so that leads us into the analysis of recursive algorithms. So much fun. So, and I told you guys this last class. We're going to kind of take a break from coding. We've coded a lot over the past 2 months. Okay, so we're going to take a little break from coding, and we're going to look at some analysis. Okay. I also told you last class that this is probably one of the, if not the most difficult things that we'll do all semester. Okay, this is not easy stuff. And I told you, I'm not telling you this to scare you, but to prepare you that it's going to take focus. Okay? So, I might have you poke your neighbor a couple times and tell him to wake up. Okay? But this is important. Not too long. This is important. Okay, so I don't want to lose you as we go through this. So, you guys know at this point, if anything is a little bit foggy as we're covering this, just stop me and I'll explain. Okay. But if you remember, earlier in the year we spent a few class periods talking about the analysis of non-recursive algorithms, which is how we take an algorithm that has a loop as its main control structure, how we take an algorithm that accomplishes whatever task, whether we have pseudocode or actual code, and we break it down and get it in big O notation. Okay, we learned how to do that for non-recursive algorithms, and we're going to do the same thing today for recursive algorithms. Now, the basic process of how we go about doing this is largely the same, but the middle step is going to be different. Okay, so let's review what we did before. The first thing we did is we always decided on an algorithm's input size. What are we passing into the function? Okay, whether it's dishes, we're washing dishes, some of the examples we did before, or we're sorting an array of numbers, or we're taking a single number and doing something with it. We have to look at what the input is. Okay? The second thing we do is we have to figure out what the basic operation is. What operation inside the algorithm contributes most to its total runtime? Is it a comparison? Are we multiplying? What is it that we're doing that's taking up the most? Okay? Now, at this point in time, once we figure out what the basic operation is, if we're doing a non-recursive algorithm, this is where we would set up a summation that reflects the total times that the basic operation runs. Okay? The summation reflects the looping structure. But when we have recursive algorithms, like this one, which we'll talk about in a second, there's no loop here. So because there's no loop here, we can't set up a summation to reflect that control structure. Okay? So this third step is going to be different from what we did with non-recursive algorithms. In this situation, we're going to set up what is called a recurrence, or a recurrence relation. Okay? Again, our goal here is to identify the number of times the basic operation runs based off of the input size. Once we solve that, then we'll get the algorithm expressed in functional notation. We'll pick out the dominant term. We'll put the dominant term inside of big O. Okay, which we've done that before. Okay? That shouldn't be anything new. Any questions before we get into this? Everybody ready? Excited? Yes. One person. That's good. All right, so let's do this. I'm going to draw this over.
No.
Oh, okay. So we've got a recursive function. Okay. Where, if you can see on the TV, we've got if n equals 0, we'll just call this f. F for function. If n equals 0, or is it return 1? Else return the f of n minus 1 times n. Thank you. Okay, so here's our function. How do we know this is recursive? Here, I'm good at spelling. How do we know it's recursive? What's the name of the function? F. Well, it was function, then I erased it. That's just F. So how do we know it's recursive? It calls itself, right? It calls itself right here. So, where's the base case? Good. Recursive case. Here. Good so far? Okay. So, step 1, what's the input size? What's the input and what's the input size? N. Some number n. It's a basic operation. This is tricky. What's a basic operation?
Oh, it's if n equals the comparison.
Keep going. We almost have everything listed. It's tough. So in the past, a lot of times we do comparisons as our basic operation. We got a variable compared to a constant. So again, getting into what the basic operation is a little bit beyond the scope of this class. Okay, when we get into tricky stuff like this. Long story short, we're going to focus on, because of the nature of this function, we're going to say that the basic operation here is this multiplication. And if you mess up in life and you pick the wrong basic operation, 99 times out of 100, you're still going to get the same answer. Okay. Advising appointment.
Wait.
Bless you. If you haven't signed up for an appointment with your advisor, make sure you do that. Don't be that person that emails your advisor 2 months from now. Oh, I forgot to register for class. No, don't be that person. All right, so step 2, identify the basic operation. We said it's the multiplication down here. Step 3, again, in non-recursive algorithms, this is where we would set up a summation, where we would say, we'll denote that the basic operation multiplication is n. Okay? So the number of times we multiply, based off of input size n, equals, and this is where we would draw the summation and solve the summation. All right, you guys remember that? Please say yes.
Yes.
Good, thank you. I was on your test, your midterm. You did those in your midterm. They'll be on your final too, so don't forget them. So we still want to accomplish the same thing. We still want to get this expressed in functional notation. But the manner in which we go about doing that is different because we have a recursive algorithm here instead. So what we're going to do is 2 things. The first thing that we need to do is set up what is called a recurrence relation, or just a recurrence. Okay. A recurrence is an expression, you write this down, it's an expression of a function in terms of itself at another point. It's an expression of a function in terms of itself at another point. Expression of a function in terms of itself at another point. Now you wrote down that definition, but it really doesn't help you understand what it is. Did you bring me some food?
I got you next week.
Yeah, appreciate it. It's an expression of a function in terms of itself at another point. So that's helpful because that doesn't really tell us anything. So the best way to really understand this is just to look at an example. Okay? I'm going to move this over a little bit. So, step 3. We're going to set up a recurrence that reflects the number of times the basic operation runs. Okay. So, recurrences are always in terms of their self at another point. So, when we're talking about in terms of itself, we're talking about in terms of the name of the function. We're trying to figure out how many times we multiply. And this is where it gets tricky. Okay, so if you're sleeping, wake up. Or I guess if you're sleeping, you can't wake. Tell your neighbor to wake you.
If you're sleeping, how do you tell your neighbor?
Hey, there's flawed logic in that request. Hopefully my flawed logic was funny enough for you to wake up. Yeah. Unless you're sleeping. Look here, because this is important. It's expressed in terms of itself. M of something equals M of something. It's defined, it's expressed in terms of itself. Part of its definition is itself. Okay? Now, there will always be 2 parts to fill in a recurrence. Part 1, part 2. The first part is derived from the value, and you write this down. Look at the value that the input size changes.
You said that one time.
Sure. The first part of our recurrence, so inside the parentheses for technical terms, look at how the input size changes when a recursive call is made. Look at how the input size changes when a recursive call is made. So somebody look at how the input size changes when a recursive call is made. What happens to it? Goes down by 1. So watch this. Easy enough? What do you think you would put here if this were n minus 2? Say n minus 2.
N minus 2.
Very good. It's simple. What do we change by here? You plug this in up here. Okay. Now here's where logic comes into play. See if you guys can figure this out. We'll read this in English. The number of times we multiply at input size n is equal to the number of times we multiply when n is 1 less. Does that make sense? Now, is that logically accurate? Okay, so look at what this does. Anybody figure out what this does yet? Yes, factorial. It recursively computes n factorial. So, what is 4 factorial? Right? What is 5 factorial? Or, right? So, the number of times we multiply when the input size is 4 is how many? According to the code. So, pass in 4, multiply when it is 4, goes to 3, goes to 2, goes to 1. Plus 1. So here's the point. Let's just say we do this. Is this right? Now what's the right answer? Again, here's how you read this. This isn't saying what is 4 factorial. This is saying, this is a function that says we multiply this many times at this input size. So how many times do we multiply when the input size is 4? 4. So how many times do we multiply when the input size is 5? How many times do we multiply when the input size is 100? Stay with me. How many times do we multiply when the input size is n? Now look at this. We said if n is 100, we multiply 100 times. But the way this starts out is if m is 100, that's the same as 99? No. We have to add on something else. What do we add on?
You did 5 times 4 factorial, so would it make sense for it to be n?
Eventually, yes, but we're not there yet. All right? What do we add on? All right, were you answering this question, or were you asking something else? Yeah. What do we add on here? Now, remember, this is the number of times we multiply, not the actual value that we get in terms of factorial. So how many times do we multiply between 99 and 100? Don't ever think it. 1. Again, what makes this confusing is that we naturally want to solve the factorial. We're naturally trying to solve this, but that's not what we're doing here. We're trying to get the number of times the basic operation executes. Yes?
So that 1 represents 1 multiplication?
Yes, exactly. Okay? And that's the second point. So I told you how to get this first point. To get this first point, you look at when we make a recursive call, and you look at the value that the input size changes. The input size has to change. If the input size never changes, then the base case never gets reached, and you have infinite recursion. Okay, so the input size has to change. So you look at how it changes, and you plug that value in here. To get the second part, you do this. Write this down. Look at how many basic operations occur at each recursive call. Look at how many basic operations occur at each recursive call. Look at how many basic operations occur at each recursive call. So how many times do we multiply here? Each time we make a recursive call.
N time?
Look at a single instance of the call. Once. Right here. The only place we multiply. So each time we make a recursive call, we multiply 1 time. So if we make 100 recursive calls, we do 100 multiplications. If we do 99 recursive calls, we do 99 multiplications. Well, you guys learned a long time ago that this isn't good. 100 does not equal 99. So we have to tack on another value to make them the same, right? And when we look at this, we're outside the realm of computer science in terms of this is not an assignment operator. So this has to be equal to this, equivalent, both sides. Okay. Are we good so far? Okay, so this begs the question, why are we doing this? Like, we have proved that 100 equals 99 plus 1. Or 5 equals 4 plus 1. Took a long time to do that. Well, what's the point of this? We're going to get there. So poke your neighbor, tell them to wake up. Gently. They give you a mean look, don't actually point. So, what we have done is we have set up our recurrence. Okay, our recurrence, my eraser. Our recurrence is m of n equals m of n minus 1 plus 1. This is an expression that tells us the number of times we multiply. Okay? But this is only one part of what we need to do. The next thing we need to do is we need to set up what is called an initial condition. We set up this recurrence, and this is great, but in and of itself, it doesn't tell us anything. It shows us how the recursive calls change the input with respect to how many times we run the basic operation, but we can't do anything with just this. What we need is an actual number in terms of an input size and how many multiplications we perform at that input size. All right? So the next thing we're going to do is we're going to set up an initial condition. Again, there are 2 parts. Part 1, part 2. So what we're trying to do here is we're trying to establish a specific input size. So an actual number here. We're not talking about in terms of n. We're talking about an actual input size, like 7 or 4 or 2 or 1 or a million. And we want to be able to determine exactly how many basic operations occur at that point. So here's how we do this. We look at when the base case occurs. Who can tell me at what input size the base case occurs?
Oh, zero.
At what, yeah, 0. At what input size does the base case occur? We know our input is n, so at what value of n does the base case occur? 0. Part 1. At what input size does the base case occur? You good? Good? You just realized what? You know what I'm doing next? I'm just saying. You got it. So, part 1. The value of the input when the base case occurs. Part 2. How many times do we multiply when the base case occurs? 0. We multiply 0 times when the base case occurs. How do we know we multiply 0 times? Well, when the base case occurs, this is what happens. There's no multiplication there. We return a value, and the value eventually gets multiplied here. Well, we don't multiply. In this instance of the method, in this version, when we call it, when the base case occurs, no multiplications occur. Okay. So, the way we read this initial condition, the number of multiplications when the input size is 0 is 0. We multiply 0 times when the input size is 0. Questions on that? Are we good so far? I would say we're getting close, but we're really about halfway through. Okay. Very good. So what we have done is we've set up a recurrence and we've set up our initial condition. Now we need to solve the recurrence. Okay? The way we solve the recurrence is solve. The way we solve the recurrence is by using what is called backwards substitution. Backwards substitution. Sounds like a math term. So what we're effectively going to do is utilize the same principle that we use to establish the recurrence to break this out. And the goal with applying backward substitution is to identify a pattern. We are looking for a pattern to emerge. Okay? What are we doing with backward substitution? We're looking for what? Pattern. So here's how this works. We said m of n equals m of n minus 1 plus 1. We've established that already. 100 equals 99 plus 1. So what I'm going to do here, the way I'm going to apply this backward substitution, let me do it like this. I'm going to take m of n minus 1, and I'm going to substitute in its place the next recursive call that would occur after it. So we started with m of n. The next recursive call was m of n minus 1. We had to tack on plus 1 to make these the same. Would you agree that m of n minus 1 is the same as m of n minus 2 plus 1? Would you agree that this is the same of m of n minus 1? Say yes. Very smart. Again, this is like saying, when we compare this, we multiply 100 times here, It's the same thing as if we multiplied 98 times, because we did minus 2, plus 1, which got us to m of n minus 1. And then this plus 1 up here gets carried down. Okay? So this part in green, we substituted for m of n minus 1. In its place, we put m of n minus 2 plus 1. Now this plus 1 got carried down. So what we have now is m of n minus 2. 1 plus 1 is?
2.
Good. Do we agree with this? Still good? Okay. Let's keep going. Why are we doing this again? What are we looking for? Pattern. Good. We're looking for pattern. We need a couple before we can look at before we're going to identify a pattern. So now we're going to substitute the next recursive call. So we take m of n minus 2. What's 1 after 2? 3. So we're going to sub in the next recursive call, which is n minus 3 plus 1. Now this plus 2 from above gets carried down. Okay? And we get m of m minus 3 plus 3. 100 equals 97 plus 3. Again, this isn't anything groundbreaking. We're not discovering any new math proofs or anything like that. But we've said already, what we are doing is we are looking for a pattern. Can we identify a pattern at this point?
Yes.
Kind of? What do you see?
As it continues to go down, the constant continues to go up.
Good. So we could say that this gets simplified. M of n equals what? M of n minus I plus I. Where I is the number. It goes 1 to 2 to 3. And as this one goes up, so does the one on the end. 1 to 2 to 3. Yes, sir?
So when does the recursion end? If
We could do this forever.
that's all.
Okay? And that's why at the beginning I said we are doing this to look for a pattern. Okay? Typically speaking, you won't have to do a ton of these before a pattern starts to emerge. Okay? But we could do this forever. M of n minus 3 billion plus 3 billion would be the same thing. We're looking for the relationship between decreasing the input size and the number of basic operations that we add on to it. Because this side has to be equal to this side. So as we change these values, how does it balance itself out so that it still equals this side? Okay? So now we have used backward substitution to identify a pattern. There's one more step to go, and then we're done. Okay? Now, what we have here is a nice statement that's defined in terms of itself. Remember in English class, when you guys were younger, or even now, they asked you the definition of a word, and you use part of the word in defining the word, and they yell at you for that? You know what I'm talking about? That's what we do here. We're defining the function m, the number of times we multiply, in terms of itself. And in terms of use, we can't do anything with this. So the last step that we have to do is we have to get rid of the m of on this side. We have to get rid of this m of n minus I. We have to get rid of this. Because we can't define it in terms of itself. Does that make sense? Here's how we do that. We use the recurrence We used our recurrence, and we used backward substitution to identify a pattern in the recurrence. We haven't used the initial condition yet. And what we want is we want to get rid of this. And so here's the key. If we can get this, m of n minus I, to equal this, m of 0, then we can plug in 0 for this. Right? Let me see that again. Get some confused ones. We know that our goal, can you guys see this in the back? Kind of. I'll write it higher. Our goal is to get rid of the m of here. We've got to get rid of this. The way that we do that is if we can get this, specifically what's on the inside of the parentheses, if we can get what's on the inside of the parentheses to equal this, then we can simply plug in this. Do we see that now? Because the point of the initial condition was not to talk about how many times we multiply in terms of some unknown number n, but in terms of a specific value. When the input size is 0, we multiply 0 times. So if by some math miracle we can get n minus I to equal 0, then we can plug in 0 for this whole thing. Make sense? Everybody understand that concept before we figure out how we do that? Everybody good with that? Yes?
Would you repeat it again?
Sure. Our goal is to get what is on the inside here, n minus I. Our goal is to get that to equal 0. Because if it does, we've already established that m of 0 results in 0. So if we can get m of 0 here, we can replace that with 0. Okay? And that gets rid of m of, because we've got to get rid of that. Okay? So, we know, here's how we do it. We know that we can have any value here for I. We can have 8, we can have 432, we can have 1,000,000,000,000. Doesn't matter. We can have any number there. But whatever number we have here, we have to have here. So, what can we plug in for I so that we get 0 here? Somebody said it. N minus 0 is n. So what can we subtract from n to get 0? N. We plugged in n for I here, so what do we plug in here?
N.
Right? Any questions on what just happened? Yes?
So you're substituting I with n.
Yes.
The number of times the basic operation occurs, you're giving it that number, it's going to be the input size.
Yeah, we just so happen to pick n. Remember, I can be any number.
Yeah.
And our goal was to get this to be 0. That's why we picked n.
It could have been like m of 14 minus whatever.
Correct.
Okay.
Absolutely. Yep. Other questions? This is the recurrence solved. It's the same thing that we get when we solve a summation. We get the functional notation of the algorithm. Expression, functional notation now. From here, we know what to do. We pick out the dominant term, we put the dominant term inside big O. Really simple. What's the order of growth? ON. Now, you guys could have probably looked at this and told me in 10 seconds what it was. But now we proved it. That's it. Questions on this? You guys good?
Yes.
Ready to try one yourself?
No.
Yes, you are. All right, here's what we're going to do. It's not cooperating.
I'm doing stupid stuff today. See if the copy.
All right, we got about 15 minutes. So I need to end a few minutes early.
See that? I'll figure it out.
All right, so this topic outline is posted on Canvas for you guys. You can check it out there. It explains in a little bit of detail what we just did. I'll post the video to Canvas as well, but you can check out kind of a written explanation of what we did. But I want you guys to try one on your own, okay? So, I've told you this before, let me tell you again. When you're doing these problems in class, you know we're going to go over them, okay? You will get the most out of it if you struggle with it. Like, obviously, if you can solve it, you're in great shape. Perfect. But if you don't know how to do this, don't just give up. You've got to struggle with it so that when we actually go over the answer, you know where it is that you got stuck and you know what to pay attention for. Okay? You know what questions to ask. Okay? Try this one on your own. Giving you a recurrence, giving you an initial condition, where you should start with backward substitution. Okay? Identify a pattern. Once you get the pattern, plug in I. Try to get that to equal the initial condition. Take a couple minutes and do this one.
Is it possible you can make it like a little bigger?
Is that big enough? Oh, good. See?
No, it's not big enough.
Too small.
Too small?
Can you make it any bigger?
Good one, okay.
It's really hard to read that font.
And the color on the old person.
Can you change the font to Old English?
I only read red.
That red line is distracting me.
You guys want to throw on tape, I can't throw it.
I mean, you can always edit it out.
That's true. That's true.
It'd be annoying. It's a lot, yeah.
right, we'll just take one more minute. We'll go through this. All right, let's go over it. If you're not finished, that's okay. So, we're starting with backward substitution. And our goal here is to identify a pattern. So what we're doing is we're plugging in the next recursive call, making sure that both sides still stay the same. So what we've got is a of n minus 2. And in its place, we're going to plug in the next recursive call, which would be what?
A to the n minus 4
Very good.
plus
A, n minus 2 plus 2, and then this plus 2 gets carried down. So we get plus 4. Okay? We'll simplify this.
2. Should that be n minus 4? Or is that n minus 2 again?
We'll add them together. Here. A, n, I'm sorry.
Yes.
You got it. N minus 4 plus 4. Sub in the next, which would be a, n minus 6 plus 2. This plus 4 gets carried down. Simplified. Pattern, just like the one we did before. Okay? We started with n minus 2 plus 2. We got n minus 4 plus 4. Then we got n minus 6 plus 6. Simplified, a of n equals an minus I plus I. Just like before. Okay? I wanted to give you one that was similar, but still a little bit different. Yes, sir?
Is it 2i or just I?
It's just I.
Why? Is that
If you have 2i, n minus 2i, it has to be 2i out here. And again, that's fine because I can be any number. So whether you plug in 6 or 3 times 2, it's the same thing.
It's going to be 2n, which is the...
Exactly.
Okay.
So 2i is not wrong, but because it represents any number, it's the same thing. But yeah.
Why are you decreasing your basic operation by 2 as opposed to like 1?
Because we know, based off of the definition of a recurrence, the value that we have here is the value that the input size shrinks each time. And so because we know it goes down by 2, it can't go down by 1, by definition.
Oh, gotcha.
Does that make sense?
Yeah.
Okay. What's
So
up?
because of that understanding, we can't, that it still makes it a to the I, or n minus I. It doesn't matter how many times you do it down, you're still going down by 1 each time.
Right. And again, it doesn't matter how many we're going down each time. If we're going down by 6 or 40, what we're doing, we're looking for a pattern. Yeah, so what we really care about is this number is the same as this number. So this number, the I, is the same as that number. Whatever it is, those two numbers are the same. All right? So now once we have this, our goal is to get rid of this. And the way we get rid of it is by looking at our initial condition. We want it to equal what? Very good. A of 1. And so we ask ourselves, we have n minus I. Plug in for I so that this equals 1. Very good. N minus 1. Okay, so we get equals A of n minus 1 plus n minus 1. Simplifies to A of 1 plus n minus 1. Because we have A of 1 here, we can plug in the value of 0, and we get 0 plus n minus 1, which ultimately breaks down to n minus 1. We've got it now in functional notation. Pick out the dominant term. The minus 1 gets ignored because it's a constant. We get O n. Okay. See, this stuff's not hard. Now, here's the thing. Questions first? Yes, sir.
Why did you do n minus 1 again?
Because that's the value that we had to plug in for I to get A of n minus I to equal 1. So look here. This is what we had. We said we needed to get rid of this. Okay? So we had A of n minus I. And we had to figure out, we know that we're going to plug in some value for I. And so the value that we pick needs to make sure that whatever value we plug in here, when we say n minus that value, we get 1. And the reason we want 1 is because when we look here at our initial condition, it's specified at input size 1. So we know when input size 1 occurs, we can plug in the value of 0. So when we plug in n minus 1 for I, n minus that number minus 1 leaves you with 1. This gives us this. A of 1 is 0, and that's how we get this. Did that answer your question? It's a lot to look at once.
I guess I'm easier with numbers. I actually have numbers as opposed to variables.
Algorithm analysis is not everyone's cup of tea. So you have to do it in terms of n. What's up?
So big O is the n minus 1.
Just be O n. The minus 1 gets ignored. Okay? Questions on this? Now, there are a couple more practice ones. I want to give you a heads up what we're doing. So next class on Tuesday, we are going to review this. We will do a couple more practice problems, and we're also going to look at tree traversals, which are done recursively. Okay? This is all in preparation for our next data structure, which is binary search trees. Okay? Fun stuff. Questions?